And we are back. Welcome back from Tuesday. Today, we're going to continue on with our conversation about calculating confidence intervals. But before we get started, let's deal with some administrative bits. And the reading for all of this is section 9.2 to 9.2.1 in the main text. It's only two and a half pages. Please make sure you are through that. We will be having a written exam number 2. It will be formatted as 24-hour take-home. It will start on Tuesday's class opening on the 21st at 9:30 in the morning. That's Tuesday. And it will be auto-released at 9:30 in the morning. We will meet online for that class period where we will discuss the exam and I can field any questions you might have for that. It will close 24 hours later, which will be Wednesday the 22nd at 9:30 a.m. Please make note that it's not 11:59 and 59 seconds. It is at class meeting it's released, and at class meeting 9:30 in the morning it closes. Please make sure you're managing your dates and your time. This is to be an individual effort. It is an exam, and you will be signing and submitting an honesty statement that you will not be collaborating with others on this. You're free to look things up to help you. Please cite your sources, but you cannot collaborate with another person in the class. If I see two solutions that are clearly the same, I will give both parties a 0 or all parties a 0, no questions asked. And so with trust comes responsibility. I treat you as a professional, and I expect you to comport yourself likewise as a professional. Okay, so when we last left off, we talked about this idea of using the central limit theorem, and if we compute a statistic over a set of samples, it did not matter what the distribution of that set of samples is, we can make it look like a normal distribution. And unfortunately, on this slide, I do not have that typo corrected. Here we have Sn, which is the sum of n many samples from a distribution. X1 is the first sample, and we're going to add them together up to including Xn. So if we have a statistic, and that statistic involves a sum, then the distribution of that statistic will look like a normal. And so we talked about that and proved that, and we also demonstrated that in MATLAB last time. Okay, I won't repeat that. I'll leave that to you to look back at the previous screencast. All right, so let's continue on. We have our standard normal distribution, and at least I'm consistent here with my typos. That should be Xn. So we have our normal distribution, and we want to make good comparative measures. And let's assume we have samples from two drastically different distributions. The example we gave before was a Poisson distribution, and we had an exponential distribution. A Poisson is a discrete distribution. It deals with the number of events observed in time. It is also, well, the exponential distribution, I should say, is a continuous distribution. It deals with the amount of time that transpires between events. That is a continuous distribution. We take samples from them. They're just two completely different distributions. But if we compute the sum of a bunch of Poisson samples and a bunch of exponential samples, those sums are both normal, and we showed that. So we can make these samples from these two different distributions normal by making use or taking advantage of the central limit theorem. And we showed that, and it's also in the Barron text, and we also did that last semester in stochastic computing. So let's try to make comparisons. Let's assume this normal curve is a result of computing a statistic involving a sum originally sampled from a Poisson. And let's assume that this other normal curve was computed from a statistic involving a sum for the exponential. And just to be absolutely correct, let me fix that typo once again. And we have two different normal distributions. They were both arrived upon by calculating a sum or some statistic involving a sum for original samples that were from a Poisson and from an exponential. And as such, by the central limit theorem, we have a particular mean of the normal derived from the Poisson samples of n1 mu1, and then we have the variance of n1 sigma 1 squared. And for the exponential, that corresponds to a different normal distribution, and it's different because it was arrived upon by sums or statistic involving sum from an exponential. That's going to have a different mean, n2 mu2, and a different variance, n2 sigma 2 squared. Okay, so we have these and we want to make comparisons. And I just changed the example. Let me go back. And instead of saying the Poisson and the exponential, let's assume that you have 100 temperatures that you've measured over the course of one day. All right. And then let's also assume you have a Poisson. So that would be a normal distribution. And then we also have a Poisson. And we can make that Poisson look like a normal, and a normal is already normal. So let's assume we have two means and variances. So that's the mean, and that's a variance. And we have a mean here and a variance corresponding to the Poisson that we arrived upon when we calculated the statistic involving a sum. Okay, so we do that. And let's just assume, I mean, yes, the normal is a normal, temperature is normal to begin with, but let's just assume we computed a sum and we say, okay, well, that's our normal. This is its mean and this is its variance. And likewise for the Poisson version of the normal, you get by using the central limit theorem, this is its mean and this is its variance. And so let's say the first distribution, the one on the left, that normal, it corresponds to 100 temperatures that you've taken over a one-day period of time. And let's assume for the Poisson, that sum corresponds to 400 customer visits over a cumulative time frame of, let's say, 2 days. Okay. So you want to make comparisons between this first system, that system of temperatures, and the second system, that statistic computed over a system of arrivals or visits in time. Now, if you're going to do that, well, is there anything wrong with this? What do you think? Please press pause. Think about it and come up with your answer, and we'll talk about it. Okay, so before we press pause, we asked if there's anything wrong with making comparisons between these two systems, the 100 temperatures over a day and the 400 customer visits over 2 days. Well, for one, we noticed that the means are different. So the location of this first distribution, the temperatures, that's different. And also the dispersion, the square root of the variance, sigma 1 times radical n1. That's just the square root of the variance is a standard deviation. That dispersion is much larger than the dispersion for the second, the arrivals, the second normal distribution. For that, the mean is n2 mu2, so it's a different location, right? n1 mu1 might be a little bit to the left or to the right, but it's different nonetheless, to the left or right of n2 mu2. And likewise, the dispersion, in this case, of the second distribution is smaller than the dispersion of the first one. So if you want to make comparisons, it's really hard to make comparisons because they're centered differently, their mean, and their dispersion is different. So we need to cast these in a similar way to what percentages does. We need to cast them in the same scale so that we can make a fair comparison. Okay, so what is wrong with this? Well, for one, n can be different, okay? The mean can be different, as we said, and because the variance is different, the standard deviation is also different. So it's really hard to make a comparison. In similar fashion, if you said $100 a share security, it increased to 125, well, that 125, that represents a $25 increase, that amount. And let's say you had a $50 stock or security and it increased to 75. Well, that represents also a $25 increase. In the first case, well, that represents a 25% increase, but in the second case, that represents a 50% increase. So even though the number is the same, the scale is different because that 25 increase means a bigger percentage change. And so this idea of a percent says, let's express this change relative to a scale of 100 out of 100. And so if you do that, okay, well, you're effectively normalizing it, putting them on the same scale, if you will, and then comparing the change relative to that per 100 scale. So on a per 100 scale, this increased 25 out of 100, and on a 100 scale, this increased 50 out of 100, even though it's $25 change each. So it's really important to express quantities if you're going to make a fair comparison, to express those comparisons on the same scale. Okay, and so because n can be different, the mean can be different, and the standard deviation can be different, you can't really make a fair comparison by just looking at the size of the dispersion, for example. Okay, so you can't make a fair comparison between the two because they're on different scales, and moreover, the average is different. They're centered differently. So how can we do this? Okay, well, to make a fair comparison, what is our solution? What do you propose to do? Well, one of the things we can do is we can say, okay, let's center these distributions. Let's make the centers the same. And you do that by, instead of centering them at their respective means, you're going to center this one at origin at 0, and you're going to center this one at origin at 0. So how do you do that? Well, that means this mean has to be at the origin. So you're going to subtract the mean from not just that data point, from every data point you have, and that has the effect of shifting this distribution so that it's now centered at origin. Same thing here. You subtract n2 mu2 from every data point for this distribution, and you effectively shift it to the left so that its mean is now centered at origin, and now the mean is going to be 0 for the right-hand distribution, and the mean is going to be 0 for the left-hand distribution. Okay, so you put them on equal footing, and how do you do this? Well, for each measurement that you have corresponding to those distributions, you're going to subtract the mean. So that means for the left-hand distribution, you subtract n1 mu1, and for the right-hand distribution, you subtract n2 mu2. Now remember, these are the distributions over that statistic that involve the sum xn, and this one is also a statistic that involves a sum x1, xn. It just so happens that this xi comes from a Poisson governed by some unknown parameter lambda, and it just so happens that this xi came from a normal distribution governed by some mu and some sigma squared. Okay, so by subtracting the mean from this every data point from the sampling distribution and the mean from every data point of this sampling distribution, you're effectively recentering it, shifting the distribution so that the mean is at origin. Okay, so now when you center it, well, what happens? It's now centered at origin, but the dispersion is still different for both of them. They're not on the same scale. Well, now you're going to divide the standard deviation. You're going to divide each data point, rather, once you've subtracted the mean. You take all those results, and you subtract each one of those results, the result of this second bulleted step, that second step, step 2 here. You're going to take the result of step 2 in both cases, and then you're going to divide by the standard deviation. So what does that do? If you divide by the standard deviation, you're basically shrinking this distribution. It's still centered about origin, but now it's going to be shrunking in about the origin. Likewise, this one is going to be shrunken in about the origin. And dividing by the standard deviation is such that when you shrink it in, the new standard deviation is no longer, for the second distribution, it's no longer going to be sigma 2 radical n2. The standard deviation is going to be 1. And therefore, the variance is going to be 1 because the variance is the square of the standard deviation. And likewise, the standard deviation for this one is also going to be 1. Okay. And the variance is also going to be 1. So now what this means is that the new set of measurements or points from this distribution is going to be a normal that hasn't changed from the central limit theorem, but we've changed the mean, mu, to be equal to 0, where before it was n1 mu1, and we've shrunken down the standard deviation down to 1. And so now the variance, which is the square standard deviation, is 1. So this distribution, when you make this transformation on your data, you subtract off the mean, and then the result of that step, divide each point by the standard deviation. The resulting distribution that is normal with a mean of 0, standard deviation 1, is called the so-called standard normal distribution, right? The standard normal distribution, now you've scaled both of these normals down to the same measurement system, and now you can make fair comparisons, even though they started out as samples from a normal on the left-hand side and started out as samples from a Poisson on the right-hand side. Okay, so what types of comparisons might you make? Do they behave the same? Do they spread similar amounts of probability mass in the same locations for that new standard normal transformed form? How much probability mass falls between the range from negative 0.5, negative 0.5, to positive 0.5, for example? Now, because they started out as different normals with different dispersions, they're going to spread out probability mass in different ways over that standard or that unit or that standard deviation of 1, okay, over that range of values. And so now, because they're both standard normals, centered about origin with a variance of 1 and therefore standard deviation of 1, you can now make fair comparisons because they are like kind. They're both normals, and they're both centered at origin, and they both have a standard deviation or variance of 1. Okay, so now we can make these fair comparisons. Now, the standard normal distribution has another name you'll find in the literature. It's called a z-distribution. Now, let's recall some notation that we talked about. We talked about something called a quantile. And a quantile is nothing more than a value that partitions your distribution into a certain number of equal pieces. And so in this z-distribution, we're going to mark some values. This value is minus z alpha over 2. And this value, there's our origin, is the value on the right, is z alpha over 2. Now, this alpha is the same alpha that we talked about when we talked about confidence intervals. We said we have AB is a so-called 1 minus alpha times 100% confidence interval, right? So this alpha is sometimes called a p-value. And when we talk about this z, this is called a z-score. It's a value under the z-distribution, but this particular value we're going to call a z-score. Now, what these z-scores are, they're quantiles. And a quantile is some value that chops up your distribution into equal pieces. And so the quantile here, let's say if we chop this distribution up into 2 pieces, this is called the 0.5 quantile. It's that quantile. It's that value that chops up your distribution into 2 equal pieces. And this equal piece is 0.5 of the probability mass, that half, and that other half is another 0.5 of the probability mass. So that quantile, that 0.5 quantile. We can also define a 0.25 quantile. Those were the quartiles. So if we have our distribution here, we can divide this up into 4 pieces, and this was a quartile. This is the 0.25 quartile, and this was the second 0.25 quantile, which was 0.5. This is the third 0.25 quantile, which is 0.75 point. Okay, so here, if we talked about the 0.25 quantile, it's those values such that we divide that distribution up into equal parts that are both 0.25. Because remember, if you take the integral under the probability curve from minus to plus infinity, that probability sums to 1 if it's a discrete probability. It integrates to 1 if it's a continuous probability. So the 0.25 quantiles chop it up into 0.25, that should be 0.25, equal pieces in terms of total probability mass. And we call this the first quartile, Q1. We call that the second quartile, Q2, which is the median. We call this the third quartile, Q3. And then the fourth quartile is out here. Okay, so if we talk about this Z alpha over 2, and let's just assume alpha is equal to 0.05. Well, what is that? Okay, well, that would be the Z 0.025 quantile. Now, what is the Z 0.025 quantile? It's that quantile such that it chops up our distribution into pieces. That's our Z minus Z 0.025, which is also our alpha over 2, where alpha is equal to 0.05. That's our 0.025 quantile. So that means if we took the area under the curve in that region, that's going to be 0.025 total probability. And then the next slice is another 0.025, 0.025. And the next one's 0.025. Next one's 0.025, and so forth. And so here we have the first alpha over 2 quantile, and here we have the last alpha over 2 quantile. Now, if we have the last alpha over 2 quantile, well, the probability of this region is 0.025, and the probability of this region is also 0.025. Okay, so what does that mean? If you add up the first area under the curve corresponds to the first alpha over 2 quantile, and the area under the curve corresponds to the last alpha over 2 quantile, well, that adds up. If alpha equals 0.05, it adds up to 0.05 total probability mass. Now, if the total probability mass is 1, well, that means this region in between, that's going to be 1 minus alpha, which is 0.95 in the case where alpha equals 0.05. So what does that mean? That means the so-called tails, or the tail quantiles, if you will, want to call it that, or the z-scores associated with the tail quantiles, that sums to a total of 0.05 to alpha. And this region in the middle is 1 minus that alpha by law of total probability. Okay, and so with these z-scores, we're identifying the quantiles, and each quantile represents that proportion, which is alpha over 2 of the total probability mass for the distribution. Okay, they both sum to 1 copy of alpha 2 over 2, 1 copy of alpha over 2. That's going to be alpha. And in the case of alpha equals 0.05, that's 0.05. So the remainder in this area, that is 0.95. So why do we care about this? Well, this 0.095 probability area, remember where we talked about a confidence interval. We said if we have a confidence interval A, B, it's that region where 95% of the time alpha is going to be covered by that region. We also said, alternatively, the probability of theta rather being covered between A and B, that total probability is equal to 1 minus alpha. And so we talked about confidence interval as meaning this unknown ground truth parameter theta is covered by values within this region. And so we're now taking the standard normal distribution, and we're talking about A as being a quantile, an alpha over 2 quantile, and then B being the last alpha over 2 quantile. Now, if alpha A and B are the first and the last alpha over 2 quantile, everything that's in the middle here, that's going to represent total probability of 1 minus alpha over 2 minus alpha over 2, which is just 1 minus alpha. Okay. So this is what it's meant, this area here between these two so-called z-scores, as we call them. These z-scores are just quantiles, and the area between these two z-scores, that's going to be our confidence interval. And so you use the standard normal and the z-scores, or the quantiles of the z-distribution or standard normal, to mark the endpoints for the 1 minus alpha times 100% confidence interval. Okay? All right. It's a really, really important concept. So, quantile, recall the notation we talked about earlier in the semester, Q sub P, is that value for which the proportion P of the probability, mass, or density, depending on if you're discrete or continuous distribution, it's that value for which proportion P of the probability mass is found. So here, if we talk about alpha over 2, that's alpha over 2 of the probability, that's alpha over 2 of the probability. You add these two together, that's a total of alpha of the probability. What you're left with is 1 minus alpha. So it's the value for which P proportion of probability mass or density is found. And so minus Z alpha over 2, that Z score on the minus side, it's the minus side because it's centered at origin, so everything to the left of origin is negative, everything to the right of origin is positive. So that quantile on the left here, that is the minus Z alpha over 2. And then Z alpha over 2, that's also another quantile. Now, if you were to take the integral up to that point, right, that's going to be 1 minus alpha over 2, right? Because here, this is alpha over 2, and we have alpha over 2, the probability mass here. This region, if you were to talk about it going all the way from minus infinity to this point, that's the 1 minus alpha over 2. That's the last quantile for that particular partitioning of our distribution into equal parts, our Z distribution or standard normal. And so here, we're using the quantiles of the standard normal distribution or Z distribution. Hence, we call these things Z-scores. Okay, so a confidence interval AB satisfies the following, that this unknown parameter theta is covered by AB some percentage of the time. That means the values that theta takes on in this interval, it'll occur within this interval probability of 1 minus alpha % of the time. Okay, so a distribution we know can be made normal by computing a statistic, but that statistic has to involve a sum, right? So we can make any distribution normal by summing, okay? But it's not a fair comparison because they can have different means and different variances. So here we have mu1, n1 mu1 is different from n2 mu2, and we have n1 sigma 1 squared is different from n2 sigma 2 squared. So they can have different dispersions and different centers. So once we've made them normal by summing, well, we so-called normalize them. We cast them as a standard normal, and we do that by taking each measurement from the first distribution and second distribution. We subtract the mean, and we divide by the standard deviation. So now they're both standard normals. So we have, for the standard normal, the probability that governs the 1 minus alpha times 100% confidence interval. Okay, so we note that we want to see if an estimator falls within this region. Now, of course, we don't know where theta rather is going to be, our unknown ground truth parameter. Okay, well, we know that our estimator is going to take on one of these values. If our estimator is going to take on one of these values, we know that if we have a good enough estimator, we can get it to be really close to the unknown theta, right? The unbiasedness and consistency proof tells us that. So if that's the case, well, we want to know then, if we want a good quote-unquote confidence interval, stable estimator, something we can count on, we want some estimator that is in this range, okay? All right, so we can replace our theta with theta hat, and we have the following expression. This gives us the probability that our estimator theta hat is in this interval is going to be 1 minus alpha. So now we're going to test to see if the estimator falls within this region. Because if the estimator falls within this region, certainly the unknown parameter theta is also going to fall within this region, because our theta hat is going to be a stand in place, a good stand in place for our unknown theta. Okay, So we're going to test to see if the estimator falls within this region, some probability 1 minus alpha. All right, so the A and B endpoints, if we normalize the distribution for this estimator theta hat, these estimators are going to be the z-scores. This is going to be your minus z alpha over 2, and this is going to be your plus positive z alpha over 2, all right? So these endpoints, to be 1 minus alpha times 100% confidence interval, these endpoints are going to have to be the quantiles corresponding to the correct z-scores that gives you that 95 or 0.95 probability if you were to integrate or sum between these two regions for that distribution or that probability. Okay, so the A and B endpoints are the z-scores for the normalized version of the data. So let's go ahead and normalize it. Well, we're going to replace A with minus z alpha over 2. We're going to replace B with plus z alpha over 2. And then we're going to subtract off from each estimator data point, because remember, we're talking about the sampling distribution. So we're going to take our estimator, we're going to subtract off the mean of the estimator, so E of theta hat, we write theta hat minus E of theta hat, and then we're going to divide that result by the standard deviation or the standard error of that estimator. Okay, so we have this expression here. Now we're going to do a little bit of mathematics. So we know that E of theta hat, if you have an unbiased estimator, that's going to equal theta. So we're going to replace this E of theta hat with theta. Okay, so we then take this expression and we're going to multiply both sides of inequalities by this sigma of theta hat, by the standard error of theta hat. So we have this expression and we have two inequalities. We have the inequality on the left-hand side and we have the inequality on the right-hand side. And so if I multiply this term in the middle by theta hat, right, if I say times sigma of theta hat, I have to also multiply this side times sigma of theta hat. Now, if I multiply this one, I also have to multiply that inequality by the standard error of theta hat. Okay, so I do that, this multiplication cancels out with that multiplication, and then I'm left with this z-score minus z alpha over 2 times the standard error of theta hat, and I am left on this side with positive z alpha over 2 times the standard error of theta hat. Okay, so I do that multiplication, and I'm left in the center with theta hat minus theta, because remember, that expectation is nothing more than theta. If my estimator is unbiased and consistent, that is absolutely true. Okay, so now I've multiplied both sides of these inequalities, the inequality on the left, inequality on the right, by this sigma of theta hat, the standard error of theta hat. And now I'm going to isolate this theta by subtracting from both sides of these inequalities. I'm going to subtract theta hat. So I'm going to take this expression and I'm going to subtract minus theta hat from the center term. I'm going to subtract theta hat from this right-hand side of the inequality, and I'm going to subtract theta hat from this left-hand side of the inequality. So I have a minus theta hat minus this z over alpha times the standard error of theta hat. I have this theta hat that's negative, this theta hat's positive, so those are going to go to 0. I'm left with the minus theta in the center. And then I have this minus theta, and I have plus z alpha over 2 times standard error of theta hat. Okay, so I rewrite that. Here's my minus theta hat, my minus my z-score for my first quantile, and I have my standard error of theta hat. Here I have my minus theta, and here I have my minus theta hat plus my other z-score times standard error of theta hat. Okay, so now that I subtracted theta hat from both sides, I want to isolate this theta in the center, so I'm going to multiply both sides for these inequalities on the right and the inequality on the left. I'm going to multiply all sides by negative 1. So I'm going to say times negative 1 for this. I'm going to say times negative 1 for that. And I'm going to say times negative 1 for this. So if I do that, remember, whenever you multiply by negative and you have an inequality, the inequality flips. So that's going to become a greater than equal to, and likewise this is going to become a greater than equal to. So I'm going to have minus 1 times this, greater than equal to. I'm going to have minus 1 times that minus, so it's going to be positive theta. And then I'm going to have greater than equal to, and then a minus 1 times that. So if I do that, I get this expression here. Oops. Okay, multiply by negative 1. I do that, I get the following expression. So multiply by negative 1. All right, well, I have negative here. If I multiply by negative 1 here, well, these two minus signs go away. Okay, so that's theta hat plus my z-score times standard error of theta hat. This minus sign goes away if I multiply by negative 1. That's just theta. And this minus sign goes away, and that becomes a minus. So this becomes a positive, and this becomes a negative. So I have theta hat, positive theta hat, minus the z-score times the standard error of theta hat. And then, of course, this less than equal to turns to greater than equal to. This less than equal to turns to greater than equal to. So I'm left with the probability of theta hat plus z-score, standard error of theta hat, greater than equal to theta, greater than equal to theta hat minus z-score times standard error of theta hat. Okay, so given that result, I look at my expression, and I can take this and either read it this way, from left to right, or I can rewrite it so that I'm reading it off from right to left. And if I do that, I write this term first, okay, that's theta hat minus. I write the center term here, and then I have that term, which is on the other side. So if I read it off this way, I'll say this term, theta hat minus blah, 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 is less than equal to theta, less than equal to theta hat plus blah, blah, blah. Okay, so here, finally, I get, with this rewriting from right to left instead of left to right of this expression that I got from after I multiplied by minus 1, I get theta hat, the probability of theta hat minus z-score, z alpha 2, alpha over 2, standard error theta hat is less than equal to theta, less than equal to theta hat plus z-score alpha over 2, standard error of theta hat. You can also read that as saying theta, my unknown ground truth parameter, is at least greater than equal to theta hat minus this z-score times the deviation, and it's less, so it's at least this term, so it's at least that term, the theta hat minus z-score times standard error, and at most theta hat, our estimator, plus z-score times standard error. Okay, and so this defines the bounds A and B for the probabilities associated with that center region of probability 1 minus alpha. Okay, and so this is equal to, that probability is equal to 1 minus alpha. If alpha is 0.05, this is equal to the bounds A and B that define the 95% confidence interval. Okay, so what does this mean? It says, with a probability of 1 minus alpha times 100%, our ground truth parameter theta is covered by this interval AB. That's what confidence interval means. That's what we just showed. This is the confidence interval. This probability is equal to 1 minus alpha. That's the definition of confidence interval, mathematical definition. Now, the AB values, this is our A, and this is our B. That says that theta, with probability 1 minus alpha, is going to fall in this region, and that region is going to be whatever our estimator theta hat is, plus or minus the z-score times the standard error of the theta hat. Okay, so our values for the confidence interval AB, we take theta hat, a single value of our estimator theta hat, and we're going to subtract off the alpha over 2 quantile, i.e. the z-score for that particular confidence interval times the standard error of our estimator. So now we have an expression that we can use to calculate what our confidence interval AB values are. So if we have our sampling distribution, and we have a sampling distribution, as we had talked about This is a sampling distribution for some parameter theta hat. We had a bunch of values, and we know that we have a mean of the sampling distribution, and we know we have the standard error of our sampling distribution. If we have a statistic theta hat which takes on some value, well, how do we compute A for the confidence interval AB? Well, we compute A by just subtracting off the z-score for the standard normal associated with a certain confidence level times the standard deviation of theta hat. So we take the standard deviation or standard error. We know what that is. This standard error, that's our sigma of theta hat. We know what that is. We look up the z-score for alpha. We choose our alpha confidence level, and we look up the z-score plus and minus z alpha over 2, right? We look that up, and then we just calculate A is equal to theta hat minus the z alpha over 2 times standard error of theta hat, and B is equal to theta hat plus our z-score for the alpha equal over 2 times the standard error of theta hat. And this gives us a confidence interval. And if alpha is equal to 0.05, that means we're going to look up the z-score plus or minus for 0.025. And once we look that up, there's some standard tables that you can look up for confidence intervals. This will give us what the AB is, and you're guaranteed that regardless of what your unknown theta is, 95% of the time, regardless of what this AB is, because it's going to change if you use another theta or another theta hat or another theta hat, this AB is going to change. But if alpha is 0.05, you know that regardless of what AB is, right? AB could be this interval, it could change to that interval, it could change to that interval. Regardless of what your AB interval is, if alpha is equal to 0.05, that means 95% of these are going to cover our ground truth unknown parameter theta. Okay? All right. So this is how you calculate the interval itself, AB, confidence interval. You need a bunch of ingredients. You need a value of your estimator, theta hat. You need the standard error for that theta hat. You can bootstrap that. And then you need the z-score for the standard normal, which are the quantiles for the standard normal or z distribution. With all of that, you can construct the confidence interval, and you know regardless of what that interval is, that unknown theta is going to fall within that 1 minus alpha percent of the time. Okay? All right. So with that, we can now test whether or not two systems are the same or whether or not a sample belongs to a system. Right? You can use these confidence intervals to draw comparisons and look at whether or not a sample from one sampling distribution matches another sampling distribution. Moreover, you can look at, for different levels of confidence, how similarly do two different distributions behave. Okay. With that, we will end there. And I look forward to Tuesday. We will go over the take-home exam, and I will answer all your questions and any questions you might have about that. I will see you all on Tuesday. Please make sure you are looking through the material and that you've understood the previous few modules. So with that, we'll end there. I will see you all on Tuesday.